Bon, bonjour tout le monde. Grand plaisir de recevoir Laura Rogers pour notre première présentation de la saison 2024. Donc, Laura a complété son doctorat à l'Université de Cambridge en UK sous la supervision de Amy Bonser en 2022. Elle poursuit depuis un stage postdoctoral au même endroit et va se joindre à l'équipe de Sixou à Tucson, en Arizona, en janvier prochain. Donc, elle est ici pour la semaine pour travailler avec moi et Erika sur son sujet qui se trouve à être les naines blanches polluées par des débris planétaires. Donc, je vais laisser la parole à Laura pour nous présenter ses travaux. Laura.
Bonjour. My French is terrible, so I'm assuming Patrick has introduced myself. And didn't say anything like, I don't know, I like balloons, who knows, whatever. But yes, hi, I am Laura Rogers. So I'm going to talk to you today about an observational perspective on white dwarf planetary systems. And none of what I do is possible without all of my wonderful collaborators. And I've listed most of them at the bottom of the slide. Hopefully this moves on. Okay, so I want to start with the solar system. And what you can see here is just a nice little schematic of the solar system. You've got the sun on the right and all of the planets that we know about. But actually, we don't really understand what all of the planets in the solar system are made from. And we can make these observations by looking at, for instance, measuring the earthquake speeds on different planets with seismometers. We can use remote observations. We can look at the atmospheres, what they're outgassing, and we can also measure the size and the mass of planets to get the bulk density. But even in our solar system, we still don't know everything about all of the planets. So we like to make things harder, so we actually go to exoplanets, and we really want to understand not just what are exoplanets made of, but how similar and different are they to planets in our own system. And so what I'm showing here is a mass radius relation, and this is the most common way that you work out what exoplanets are made from. So you measure the mass via some really actually intense radial velocity measurements that take many, many years to do. And then you can also measure the radius usually via a transit as a planet is passing in front of the star. And so once you've got your mass and radius measurements, you plot them on this diagram here, and then you compare two interior models. And so what you can see, this line here, this is from iron. So if your planet was entirely made of iron, this is the mass and radius that you would expect. And so you would end up having something that is incredibly massive and a really low radius because your density is so high. And then up here, you've got more like planets made entirely of water ice. And so you can see actually a lot of these don't really fit into this kind of ice, iron, bulk Earth-like densities. And so you often need to add additional gaseous envelopes to explain them. But this is really the best that we can do with whole exoplanets, with the admission that you can do stuff with the atmosphere, but in terms of the interiors, this is really some of the best that we can do. So in an ideal world, what I would love to do is take a planet like the Earth, smash it up into small pieces and smash it up into dust and put it into something like a mass spectrometer. And if I were to do that, this is exactly what would come out of it. So if I put the Earth into a mass spectrometer, I would work out that it was 35% iron, 30% oxygen, 15% silicon, and 13% magnesium, as well as loads of other different smaller constituents. So I'm going to save you all a lot of money, because rather than whacking planets up into dust, what we can actually do is use white dwarfs to do the hard bit for us. So we can actually use white dwarfs as mass spectrometers to work out what exoplanetary material is made from. So I know there are many white dwarf experts in the room, but just in case, what is a white dwarf? So a white dwarf is a stellar remnant, and this is the core of a low mass star that's left behind after stellar evolution. They're incredibly dense, so they have a mass of about 0.6 solar masses packed into the radius of the Earth. So this means that they have incredibly high surface gravities. So you'd only expect the lightest of elements on the surface of a white dwarf. And so what you can see here is a spectrum of a white dwarf. This is the closest white dwarf to the Earth, Sirius B. This is a DA white dwarf, which means it's basically just got hydrogen in its outer regions. And so when you look at the spectrum, you see just these really broad, deep Balmer lines, and this is from the hydrogen, and you see nothing else there. And so this is what we expect for white dwarfs. They should be nice and clean, nothing else there, except that's a lie. Actually, heavy elements are observed in about 30% of white dwarfs. And so here again, I'm showing this is a hydrogen-dominated white dwarf with metals in the atmosphere. And again, you can see flux versus wavelength. We've got our lovely, deep, broad hydrogen lines. But on top of that, you can see you've got iron lines, calcium lines, magnesium lines, lines from elements that you don't expect to be there, given what we know and understand about white dwarfs. And so this implies that there has to be some kind of ongoing accretion from an external reservoir. So many people over many years who are much more smart than I am came up with what they think is going on in these systems. So what we think is happening is you have planetesimals from the outer system. They get perturbed onto star-grazing orbits. And so they hit this radius called the Roche radius, where it basically means they can't hold themselves together anymore, and they tidally disrupt and form a disk. And so we can actually detect this based on the infrared excesses. And so here you can see a spectral energy distribution, and this is where you would expect the white dwarf to sit if you just had an isolated white dwarf with no circumstellar material around it. Whereas actually, if you start to look in the infrared, so a little bit here, this is the K band, this is one of the near infrared wave bands, and then towards the mid infrared, you see excess emission from this circumstellar material. And we now know of more than 100 white dwarfs with atmospheric pollution that also have circumstellar dust disks. So the next bit is, part of active research. So we don't understand exactly how this gas forms, but gas appears. So potentially you've got dust that's colliding and producing gas, or you've got dust that's migrating inwards via PR drag, which then sublimates and produces gas. And so far we know of 21 systems with detectable circumstellar gas in emission. And I love this schematic here because it really helps me to understand these profiles. So this is the first spectrum which shows evidence for a gas disk in emission. And you can see that there are some really broad, amazing double peaked profiles. It's really clearly an orbiting disk. And so this schematic here, I feel like it really helps to understand. So these lines are lines of constant velocity. And so as the material is going round, you've got material that's getting redshifted, moving away from you, which is causing this wing here, and blue shifted as it's moving back towards you, which is causing this wing. And then the most extreme velocities, so these really extreme wings here, are from the closest in material that's moving the fastest. And so this is what's going on with these systems. We've got some kind of Keplerian gas disk as well. So then the material accretes from this circumstellar reservoir onto the white dwarf. And this is where we use amazing instruments like Exoplanets on the VLT and many others. We use Hubble Space Telescope, all sorts of good stuff. And so we observe this material in the atmospheres of the white dwarfs. And this is where we have to work with the incredibly smart modelers like Patrick and Erica, who then model the data so that we can understand the abundances of the planetary material that's been accreted onto the white dwarf. So we can reconstruct what this body was that's come in from the outer system and then fallen onto the white dwarf. So we know what the exoplanetary material is made from. So this material then sinks down towards the core over timescales of days, essentially, for DA white dwarfs, which are these ones with a hydrogen layer. But if you've got a helium layer, which are DB white dwarfs, this can happen over much longer timescales, more like 10 to the 5 to 10 to the 6 years. But that's still shorter than the age of the white dwarf, so it still counts as active accretion. And so far, we've observed over 20 elements in the atmospheres of white dwarfs. And here is just a periodic table highlighting the different elements that have been discovered to date. And so far, most of the objects that we see that have been accreted onto white dwarfs look pretty much like bulk Earth. We've got some special ones too, which I'll talk a little bit about later. But in general, sorry to say, our Earth isn't that special. Most planetary material seems pretty Earth-like. So just to summarize so far about white dwarf planetary systems, about 30% of white dwarfs are polluted, and we have more than 1,000 that have been discovered. There are more than 100 that we have with circumstellar dust emission. There are 21 with circumstellar gas emission, and there's also a handful that have gas and absorption as well. There are about 10 known where there's active transiting material, so material transiting in front of the star, and it looks like tidally disrupted material. And I'm saying less than 5 planets because we're still not 100% sure on some of them, but roughly less than 5 planets have been discovered. So what can you actually learn from white dwarf planetary systems? So you can learn about the bulk composition of exoplanetary material, and you can actually link this back to planet formation. So understand where in the protoplanetary disk this material would have had to have formed to be able to explain the abundances that you see in the white dwarf photosphere. You can learn about the architecture and the evolution of planetary systems. You can learn about what can survive, are your belts surviving, are planets surviving, etc. So you can also learn about planetary material in extreme environments because white dwarfs are pretty extreme, to say the least. You can learn more about the geology of rocky exoplanets, and we'll cover that a little bit more later. And then you can also use them to learn about white dwarf structure and physics. And we have many experts in the room who work on this. Okay, so I'm just going to take some water. So where do I come in? So I'm an observer. I work on all sorts of things to do with white dwarf planetary systems. And so I thought I would show you a schematic here. And we're going to go for a little exploration around this diagram. And I'm going to talk to you about some of the work that I've been doing in these different areas. So we're going to start off with the planets. So I've already mentioned, we know many planets around main sequence stars. So more than 5,000, I know you said 500, 5,500 exoplanets have been discovered, but these are mostly around main sequence stars. So there's only a handful that are known around white dwarfs. So for example, there's a gas giant that was discovered via the transit method where the planet passes in front of the star and it dips. The really cool thing about this is because white dwarfs are so small that it blocked out like 60% of the light. So for anyone who works on transits, like white dwarfs are cool. That's a really cool thing to do. They had to change how they worked on these planets based on the fact that it's actually not blocking the full stellar disk. So there's also a gas giant that's been discovered via microlensing, and that was in this Blackman paper. There was an evaporating ice giant. So this was discovered indirectly via spectroscopy, which is why some people don't necessarily count it as one, hence the less than 5. And there are also some candidates that have been found via direct imaging, which is really exciting because I think JWST will do a lot to help us discover more planets around white dwarfs. So I want to highlight this plot on the right. So this is again showing mass versus, it's not radius, it's period. But what it's highlighting is the discovery techniques for most of the planets around main sequence stars. And so you can see that the transit method really does win in terms of numbers, but the second most popular, I shouldn't say popular, successful, the second most successful method is radial velocity. And so I want to talk a bit about this with white dwarfs. So just in case this is something you haven't heard about, the radial velocity method detects the presence of an orbiting planet or an orbiting companion using the Doppler shift of the spectral lines in the star. And so if you go back to our lovely DA Sirius B white dwarf, you're going to say, Laura, those are really, really broad lines. You're never going to be able to detect a planet. And I say, yes, you are entirely correct. And this is what most of the community has thought for years. Actually, you can't discover planets around white dwarfs. But I say, what if you have metal lines? And so once you have these metal lines, these are much narrower and they're much sharper. And so you can actually get down to much lower precision on your radial velocity measurements. And as part of a case study, we looked at this. So we only had a very small amount of historic data. But what we were able to show is that with metal lines, you can actually start to get down and detect like giant planets around white dwarf stars. So this was just a proof of concept. This is just showing the change of radial velocity as a function of time. And this is a plot which is showing what you would have been able to detect. So we can really rule out this area. So we would have detected it if it was there. And this has actually led to some further studies. So now we're actually going for targeted studies with Espresso, which is a very, very stable, very high resolution instrument on the VLT in Chile. And so the main thing that I want to take away from this, which I often put things in these little boxes for like key takeaway points, which is with polluted white dwarfs, you can actually search for close-in giant planets via the radial velocity method. And so one of the planets I mentioned, which was the transiting system, you would be able to discover that with a radial velocity. It would have a radial velocity signature of like 3 kilometers a second. It's huge. It's very massive. It's very close in. It's just not a polluted white dwarf. It is what we call a DC, which means there is 0 lines, not even a little hydrogen. So you can't test it. But what it means is if these planets are common around white dwarfs, we can test it. So get your telescopes doing radial velocity searches around white dwarfs. I think that there's a lot that can be done there. Cool. So now we're going to move inwards a little bit, or outwards, depending on where the planets are, and look at the dust and the gas. So these systems where you've got a polluted white dwarf with disks, and we think they're planets, they're very, very crazy, and they seem to be so dynamic. And so you may expect, therefore, to observe variability. And this has been observed. So the first example of variability was actually in 2014 by C.E. Xu and Mike Jura. And so here you're seeing the spectral energy distribution of a white dwarf. And if it was just a white dwarf with absolutely 0 circumstellar dust, it would be following this dashed line down here. And then what you can actually see, these data points, we've got an infrared excess from a disk. And so they observed this with Spitzer, I think about a year later, and they found a 35% drop in the dust emission around this object. So very interesting. People were suddenly like, hang on, maybe we thought these might have been stable, but maybe they're not. So a few additional people started to look at individual systems. So we had a GD56, which had a brightening, and then it had a decay in its infrared flux over time, which seemed to be consistent with a collisional cascade. So you've got 1228, which also has gas as well. And then 0145, which was a pretty crazy system, which increased in brightness by about a magnitude in the infrared. And again, this was followed up over time, and it was found that, again, it seemed to be, followed a collisional cascade decay. And then individual systems, amazing, tells you a lot, but we want to understand more about the population. So I'm going to talk a little bit more about the variability surveys. So here you can just see an SED in the top right. So these surveys are focusing more on the mid-infrared, which tends to be, if we just use our black body physics, cooler dust that we're assuming is slightly further out. So in the mid-infrared, you can see here, this is flux change versus baseline. This survey actually found that most systems seem to be varying on really long timescales. And so they have variability, but not just a decrease like was seen originally, but increases as well. And so in the mid-infrared, everything seems to be variable over really long baselines. So that's kind of cool. But now if we look at the near infrared, so this is where we're looking, it's basically the point where your dust is peeking out from the white dwarf. And so this, we think, is more reminiscent of this hot dust that's really close into the white dwarf, just pre-sublimation. And so what you're seeing here is, well, entirely upper limits. So we didn't find any K-band variability. So we looked at 34 stars over 3 years, and to say most of these are the same white dwarfs. And so we found no K-band variability. So it seems this close-in hot dust is probably not really varying. And so we can put limits on what you can rule out, and that's what we did here. And this line going across here is the C.E. Xu and Mike Jura 2014 result. This is how much variability they saw in the K-band. And so it shows that K-band variability is rare. And there's something interesting to say about that. And I think it might be this. So when you actually compare the near infrared and the mid infrared, if we make the assumption that the near infrared is representing this close in hot dust and your mid infrared is representing a bit further out cooler dust, then it seems as though the closer in dust is much more stable than the cooler dust, which is further out, which seems to be varying quite a lot. So we think that there must be some kind of physical processes that are acting to stabilize the disk. And hopefully this will make a little bit more sense when we tie in some other observations too. Like this one. So this is my current baby, I guess. So I've been working on this system, which is Gaia J2100, and we've been monitoring the circumstellar environment of this white dwarf. So this is a white dwarf that has pollution in the atmosphere. It's got a circumstellar dust disk and a circumstellar gas disk. And so what you can see is 4 years of observations of the gas lines. There are a number of gas lines in the system. I've just picked 2 to make it easier. And then I'm going to point out some things that I think are interesting, and I hope you do too. So firstly, so here we're looking at the evolution of the gas lines going upwards in time. So this is 4 years worth of data. There are 2 points at which the calcium lines change crazily. So this is changing by like the line fluxes are changing by like a factor of 10. And it changes very quickly and then it settles back down within about 2 weeks. So this is the fastest variability we've ever seen in a gas disk system. But you don't see this in the iron. So although you see crazy changes in the calcium, you're actually not seeing anything in the iron lines. And so here we're looking again, this is all of the profiles stacked on top of one another. So it's really clear that you can see any changes. So again, here, what we're seeing is actually the iron lines seem to go to more extreme velocities. So if we think back to that Doppler map that we were looking at earlier, the iron lines must be much closer in to the white dwarf to be able to get to these extreme velocities. And then the calcium lines, especially the ones that are in this crazy high emission state, seem to be coming from like a much lower velocities. You can also see that the calcium lines have some really asymmetric profiles. So you may be able to see it here. If not, hopefully you can see here that this actually doesn't look like a very nice, symmetric, gorgeous, equal disk. There's some really strong asymmetries in this bit, but here it's incredibly symmetric. So again, very interesting. So our current best guess is what's going on with the gas is that you've got an eccentric gas disk and you have radially dependent excitation because you have such strong flux from the white dwarf. And so there seems to be maybe this hotter inner disk where you end up exciting and getting the ion emission, and then a colder but more dynamic outer disk, which is why you end up with such extreme calcium variation. And that semi-agrees with what we saw before with the infrared surveys, because as I said, the further out the dust, it seems to be the more variable. So potentially there's this outer region of the disk is much more dynamic. It's probably got collisions and things going on. And something else that we did as part of this, this project was actually we observed the dust too. So this is a plot which at the top, this is showing the dust emission. At the bottom, this is a gas emission. So this is showing the line fluxes. And so you can see here that there were 2 points where the line fluxes increased. And this is marked by the vertical dashed lines for the calcium. And again, you can see that the iron was pretty flat. And then at the top, this is doing a similar thing, but this is for the dust. And so hopefully what you can see is now we're looking at this lovely K-band emission, which is this representing the dust disk. The dust is emitting very strongly at the same point that the gas is emitting very strongly. And this is actually the first time that anyone has observed simultaneous dust and gas emission in a white dwarf disk. So this implies that there has to be a common origin for both the gas and the dust. And it kind of the reason I was slightly hesitant in the introduction when I was talking about the gas and the dust is because there's this theory that your dust migrates inwards via PR drag. You then lose your dust and you sublimate to gas, in which case you wouldn't expect them to be correlated. So there actually has to be a mutual reason to produce the gas and the dust simultaneously. And we think it's potentially collisions. So, and that's quite exciting. So hopefully this will be out within the next month or two and you can read more about it then. Cool. So now yes.
There like some because the orbit is about 5, 6, 7 hours, I guess. So is there variability over 7 hours?
We haven't observed variability over hours, but we do over days. So it could, but we don't have a tight enough cadence.
Yeah. Side and the other side.
Yeah. And what I would really like is for really high cadence observations. It's just quite difficult to convince because when you look here, this is, or maybe even here actually, there's like an emission peak here and then another one here. And there's like 2 weeks between, and then here this is separated by a year. So it's actually quite difficult with just 2 to predict the period. And therefore, if you're going to dedicate because this is 2 8-meter class telescopes that we needed to be able to get these observations. So you really need to know when the emission peak is, and it's hard. But yes, I would love that. So the more people that are excited about it, maybe the more likely we are to get time. Cool. Yeah, so now I want to chat about some work I've been doing on actually linking the circumstellar environment to the white dwarf and thinking about what's going on in terms of the accretion events. So we've been doing a optical spectroscopy survey, and the main question that we've been asking with this is the amount of material that's in the white dwarf atmosphere constant with time? And so we're doing this by searching for variability in these metal features, in these metal absorption lines in the white dwarf atmosphere. So why may you expect there to be variability in the metal lines? And so this could be if you have accretion rate changes. So if something happened, maybe there's a big collision in the circumstellar environment, maybe you would expect there to be a sudden influx of more material onto the white dwarf. And given that the sinking timescales can be on the order of days, you should be able to see this in the white dwarf's photosphere. And there are also various white dwarf physical reasons why you might end up with variability, for example, horizontal spreading, or I'm going to just blanket it as unknown internal white dwarf mechanisms, and I'll tell you to talk to the white dwarf experts in the room as to why else you might experience variability. So we had 2 observing programs where we targeted 5 DAS white dwarfs. And so the reason we picked these white dwarfs are because they are hydrogen dominated and they have really short sinking timescales. So here you can see a plot of sinking timescale versus effective temperature. And for the coolest object in our system, the sinking timescales are 100 days, and then the rest is like 10 days. So this means if there is truly variability, we should be able to see it reflected in the white dwarf profiles. And we had data from the Magellan telescope with the Mike spectrograph from 2007 to 2011. And then we have a program that's been ongoing since 2017 using the HRS spectrograph on the SALT instrument in South Africa. So this is a lot of data. This is I can't do maths, many years, 15 years, so 16 years of data. So I'm just going to show you some data that actually was published in my thesis. And I'm just showing you for one white dwarf in particular, I've just stacked all of the data together just to see if there really is any variability between the Mike, which is the 2007 data, to the SALT data, which is 2017 plus. And so, and we think this slight difference is actually a artifact. We can talk about it if you want to, but that's fine. But anyway, so when we're looking at the actual profile of the Mike data versus the SALT data, there is just no changes. It is so similar. There's absolutely no evidence for variability in the metal lines. And this is one white dwarf, but for all 5 of the white dwarfs, except one anyway, we find that's a result. We're going to Hubble to follow that one up, so you'll have to wait a year for that. But I'll say for the four white dwarfs, then there is absolutely no evidence for any variability whatsoever. And so here, this is just plotting the equivalent width over time for some of the different lines in the spectra. And you can see that they're all consistent with basically having a flat line and showing 0 variability. And we also used white dwarf models from Patrick to actually look at whether there could be any abundance changes and what kind of limits you can get to your abundance changes. And I asked for a grid of density of like 0.2 dex, and clearly that wasn't tight enough because within 0.2 dex, all of the data lies. So there is really no abundance changes. And so what we find from this monitoring program is, yeah, there's absolutely no change in the amount of material that's in the photosphere of these white dwarfs over more than 10 years, which is thousands of sinking timescales. So that is just incredibly stable. The accretion mechanisms, the internal mechanisms, super, super stable. So based on all of this work, what have we learned about the circumstellar environment? So we know that the circumstellar environment is very dynamic. The dust that is further from the white dwarf, we think, is much more dynamic than the dust that's closer in. And we also think that the gas is being produced at the same time as the dust, which is telling us that collisions are more important potentially than migration inwards and sublimation to produce the gas, or at least the gas disk that we see in emission. We think that the inner disk, the materials leaving the inner disk at a constant rate and also arriving at the white dwarf at a constant rate. And so, yay, we've learned about the circumstellar environment, but this is really great for studies of the photosphere of the white dwarfs, because it means when we're working out what this exoplanetary material is made from, we really can trust that what's in the photosphere is what was in the composition of the parent body, with the caveat of you have to use white dwarf models and consider sinking, and it's not as easy as that. But in general, that's a good thing. Okay, so now I'm going to talk more about some work I've been doing on the actual white dwarf and thinking about the abundances in the atmospheres of the white dwarf. So I'm going back to my polluted white dwarfs are mass spectrometers for exoplanets. And a big aim of mine is to increase the number of exoplanetary bodies that we have measured bulk abundances for, so measured bulk compositions. And so this is really important for a number of reasons. One, just getting the statistics. It's so interesting to work out what any exoplanetary body is made from, but we're really trying to start to map that as a function of things like galactic location. And again, this is subject to future work, but we're really at the point where we can start to look at demographics. So I'm going to talk about two papers here, and these were actually published earlier this year. So we're studying 7 white dwarfs in particular in these 2 papers. And the reason we picked these 7 white dwarfs is because they have atmospheric pollution, a circumstellar dust disk, and also a circumstellar gas disk. So not only can we ask the question, what is the composition of the exoplanetary material that's been accreted, but we can also ask questions about systems that actually have circumstellar gas disks. There's only 21. Are they different? Is there anything that's different or interesting about the abundances or how much material they're accreting? Because again, that can inform us about these planetary systems. So this is not data. This is just a quick example to show you these confusing plots. And I'm going to break it down and hopefully it will make sense. So on the y-axis, you're going to see the abundance of X, which is an element listed across the x-axis. And it's normalized here to another element, silicon. We're usually normalized to silicon or magnesium because they are the most friendly, is the best way to say that. And so this is normalized to solar, which basically means that if your white dwarf, when you're plotting your white dwarf over the top of this, if your white dwarf has a composition exactly like the sun, then you're going to have all of your dots going straight across the center at 0. And in the solar system, icy bodies tend to have a composition very similar to solar. And so if you have something that's got a lot of, as we go over here, these more volatile elements, then yeah, it's going to look very icy, look very primitive. So this is what it would look like. And I'll say across the bottom here, these elements are ordered in increasing volatility or decreasing condensation temperature. So therefore, if you were to actually accrete something that looks kind of like bulk Earth, which is what I said lots of things look like, your more refractory elements, these are going to look very similar to solar. And then when you get more towards these more volatile elements, you're going to drop off and have what we would call a volatile depletion. And then there are other things you can look at. For example, if you have a body that was differentiated, so you have a core and a mantle, just like our Earth, and you are basically taking a chunk of that core or a chunk of that mantle and accreting it, this is a kind of abundance pattern that you would get. So your lithophilic elements would be pretty flat. And if you were accreting something that's core-like, it's got excess amounts of iron and nickel, then you would have a higher abundance ratio for these elements, and then it would drop back to being normal. And then here, if you had a mantle, you would have a depletion in those elements and then go back to being normal. So let's look at data instead. So here we're looking at one white dwarf from this survey, and hopefully you can see that this has got a depletion in iron, and also the upper limit for nickel is very constraining. So we know that it has to be quite low. And the best fit model that comes out for this is that it is accreting a mantle-like exoplanetary body. So how does that even happen? So to get a mantle-rich fragment into the atmosphere of a white dwarf, you first need to have differentiation. And so you get that when you have internal heating, which causes iron and hydrophilic elements to migrate down to the core. So this can happen during formation if you're hot enough, or even if you're just large enough, if you have a large enough body. So you end up with a differentiated body with an iron-rich core and an iron-poor mantle, just like the Earth. And then things happen in the system. So you probably have some kind of collisions or fragmentation, and this ends up leading to fragments of bodies that are either core-rich or mantle-rich. And it's these fragments that end up in the white dwarf that allows you to then look at something that's got mantle-rich or core-rich. Because if you were to accrete, both of these or something that was similar to this would just look like bulk Earth. You can't differentiate. I shouldn't say that word because it means two things. You can't tell the difference between something that's differentiated and not fragmented and something that's non-differentiated. And so this white dwarf actually adds to examples from the literature. So there's a couple where we've already seen evidence for either a core-rich fragment or a mantle-rich fragment. But this is telling us that we know differentiation is happening in other planetary systems. And we also therefore know that violent collisions must also be occurring to produce these fragments. And so it can tell you a lot. And there's some really nice literature by my advisor, Amy Bonza, on the importance of aluminium-26 to be able to get these differentiated bodies. So now we're going to look at 3 more white dwarfs in the sample. And so again, we're looking at, so this is normalized to silicon. And again, we've got our elements across the x-axis. And these are quite similar, which is why I've put them together. So again, we've got the more refractory elements roughly match a solar composition or a bulk Earth-like composition. So these pretty much match with bulk Earth and solar in this region. But as you get to the more volatile elements, I said that most things seem to look like bulk Earth, but these don't. These have a really high oxygen. So the oxygen seems to be solar or even slightly supersolar for some of these objects. But the carbon seems to be quite low. So what's going on with these? Why is the oxygen so high? So we do oxygen budgeting, which is a very, very simplistic way of essentially counting oxygen atoms and trying to work out what a body is made from. So you take your oxygen abundance from the white dwarf, and then you make a rock. So you assign it to these different oxides, such as magnesium oxide, silicon dioxide, and all of these other ones. And then you basically just say like, hey, do I have any oxygen left over? If yes, then maybe you have a water-rich body that's been accreted. No, well, it's just a rock. Yay, I formed a rock. And so what we think is going on is actually we've got a lot of excess oxygen. So maybe we're seeing water-rich bodies. And to prove this to you, this is just a fraction of oxygen assigned. So we've basically taken our oxygen and put it into all of these different oxides. We've built our rock essentially. And for these 3, once we've built the rock, we see quite a significant excess oxygen for all 3 of these. And then the one that we saw earlier, which is this mantle-rich fragment, we built a rock and there is no excess oxygen. So this is pretty much equal to 1. So this is just a rock. I shouldn't say just a rock because it's still exciting, but it's a rock without oxygen. And so in this paper, we find that there are 3 that seem to be accreting bodies that are water rich. One where the metals seem to fully be in oxide form, and this is the mantle-rich system that I showed you already. And then there's one that if I tried to plot this, it would go off the scale and probably like significantly above this room because it has so little oxygen that we don't understand it, basically. It doesn't make sense. I've spoken to geologists, all sorts of people. No one gets it. So that's the puzzle for now. But we have one that's extremely oxygen depleted. Okay, so going back to our questions. So firstly, what is the composition of the exoplanetary material accreted? Well, we've seen that 3 seem to be rich in oxygen, 1 seems to be mantle rich, 1 is kind of crazy, and the other 2 don't really have enough elements for us to say anything concrete just yet. And then the second question is, do white dwarfs with circumstellar gas emission disks resemble the general population? So I said there's only 21 systems where we see gas emission. So are they any different or are they the same? So why may you expect systems with a circumstellar gas disk and emission to be different? So potentially, you're looking at an early stage in the accretion process. So there is a paper that came out in 2022 from Mark Browers, who suggested that actually volatiles would sublimate further from the star. And if your gas composition is representing your earliest accretion stages, then you would have a volatile-rich photospheric composition. Or there are other arguments about the detectable gas may only be produced in the largest and most violent collisions, which might make sense to some of the observations we've seen before. And so there, you would expect there to be a larger amount of accretion. So we can look at something called accretion rate, which is essentially how much material is falling onto the white dwarf per second. And so the only thing I really want you to compare here is kind of orange to blue. So you're looking at systems that have gas disks in emission versus systems without gas disks in emission. And we find no evidence that systems that have a gas disks are accreting at any higher rates than those that don't have gas disks. So this is in agreement with previous studies, but because we've added 7 objects to the data set, it's quite a significant increase. It was like doubling the number with measured accretion rates. But yeah, so we really are still in small number statistics, but so far, yeah, the gas disk systems don't seem to be that special other than the fact that they have gas. But now abundances. So you can mostly ignore the central part here. So this is just looking at how the abundance ratios of the white dwarfs compare to different meteorites and things that we see in the solar system. But the most important thing here is to compare between blue and orange in these histograms on the side. And so we did some KS tests based on all different abundance ratios. And we find that there is, again, no evidence, except potentially for the volatiles, for there to be any difference in the abundances accreted by those that have gas disks versus those that do not. So let's just look a little bit at the volatiles. I mentioned volatiles. So C/O ratios in general are just like, they're really interesting because they can teach you a lot about planet formation. So depending on your C/O ratio in a protoplanetary disk, this is going to inform you of what kind of planetary bodies you're going to end up forming, whether they're going to be dominated by the silicates or carbides. And so in general, people who work on exoplanets are quite interested in C/O ratios, and we can measure that. We can measure the C/O ratios for exoplanetary bodies that are out there. And so far, so this is looking at the C/O ratio with solar is again at 0, and this is a function of the white dwarf effective temperature. And so you can see Comet Halley, CI chondrites, EH chondrites, and bulk Earth. And so just looking at the distributions, kind of fun. In general, we see the C/O ratio is pretty reminiscent of what the sort of C/O ratios that we see in the solar system. There are 2 which potentially might be supersolar, which is pretty crazy, having a supersolar C/O ratio. This one, we're unsure on the temperature. So actually, It could be supersolar or subsolar, depending on the temperature of your white dwarf. But when I got really excited about this, Patrick said to me, hang on a minute, but a dB of this temperature, you can maintain carbon in the atmosphere due to probably winds. We don't really know. So he said, yeah, I would not put that out there as a very exciting thing to say. So I put a cross through that object there, which might have been one of the really exciting, we found something that's super, super carbon rich. So who knows what the true carbon abundance for that object is, but looking at the rest of the distribution, it seems as though the carbon to oxygen ratio seems to kind of match the solar system. But gas disks seem to kind of maybe skew a little bit towards the lower end of the C to O ratio. And so I wanted to look into this a little bit more. And this plot here shows you the C to O ratio. And then on the x-axis, this is the fraction of oxygen that we have in excess. So when I was looking at those systems, trying to, make my rock and see if there's any oxygen left over, this is telling me how much oxygen is left over. And so what you can see here is we've got Comet Halley and then different chondrites in the solar system. Most of our white dwarfs lie along this really lovely kind of track where, as you have a high carbon to oxygen ratio, you've got more oxygen in excess, which makes sense because comets in the solar system will have high carbon and high water ice in the outer system, and then you kind of lose that as you get closer towards the sun. Nice little volatility trend. But there's this really weird group down here of white dwarfs that all have gas disks that don't have a very high carbon to oxygen ratio, but have excess water. I can't say much about it. It's 4 systems and our errors are large. But what I think is, I just like to say it's interesting. And we need more gas disk systems, and we need more gas disk systems that have measured abundances. And I've already spoken to a few people, and there are 2 more systems that also show a similar trend that have gas disks. So I think that there is something interesting going on. Maybe systems with gas disks are accreting more volatile rich material, or water rich material, I should say. But we don't know. So hopefully time will tell, and we can actually try and unravel these mysterious systems. So going back to these sort of hypothesis. So why may you expect systems of circumstellar gas to be different? So maybe that there's an early stage in the accretion process, and you would see that if there was a volatile rich photospheric composition. Maybe we see that. I'm not gonna, make a bet on 4 systems, but that's kind of fun. And then the other thing was, could there actually be more amounts of accretion if the gas disk systems are produced when you have the largest and most violent collisions? We find no evidence of this. As I've said, small number statistics, and we need more gas disk systems. So if anyone wants to observe white dwarfs, find us more gas disk systems, that would be awesome. Okay, so I'm going to take you back to this image just to finish up and just tell you some of the key things that I'd love you to take away from this talk. So firstly, you can use white dwarfs with the radial velocity technique to discover planets. You can't discover rocky planets, sadly, but we care about discovering planets. We have less than 5. So look for those close-in giant planets, and you can use a radial velocity technique for that. So we also find that with these circumstellar environments, we think that the dust that's slightly further out is actually more variable than the dust that is closer in. So we've also found the first evidence for simultaneous dust and gas emission in a circumstellar disk around a white dwarf. And so we think that this is suggesting that there's a common origin between the dust and the gas, potentially from something like collisions. We also find that the material is probably leaving the inner disk at a constant rate and also arriving at the white dwarf at a constant rate. We find that white dwarfs with detectable gas disks in emission, they don't accrete at higher rates compared to those that don't have them. But there's a hint that they may be accreting more volatile rich material. And finally, I really want you to take away that polluted white dwarfs can act as mass spectrometers for exoplanetary material. And so you can actually discover really interesting pieces of evidence, for example, for water-rich material that's been accreted, or iron-poor material, iron-rich material that's similar to being mantle-rich or mantle-poor. And so far, based on all of the observations of polluted white dwarfs, we find no carbon or diamond planets. So yeah, so that's it. And yeah, thank you so much for listening.